In this video, we are going to talk about kinematic expansions and how we can use the kinematic expansions to solve a problem that we have encountered before. Using BKEs, we have derived a velocity and acceleration expansions. We have two reference frames, F and G. And we have 2 points, F defined as fixed in the F frame, G as fixed in the G frame, and another point as an arbitrary point that's moving. So let's see an example. This is example 31 on the textbook, and it's the same as example 19 that we have solved before. We have an inertial frame, F frame, and we have a point that's moving with a moving support. So first of all, we need to find the velocity of point P relative to the F frame. Okay? As always, we need to find and define proper reference frames. So for this problem, we have one rotating frame. So we define a new reference frame for that rotating frame. Okay, so this bar that's rotating, so we define another reference frame that's fixed to the bar, and let's call that G1, G2, and G3. Notice that G1 is aligned with the position of the bar. Okay, and the G frame is rotating relative to the F frame with the angle theta. What we can write now is we know the angular velocity of the reference frame G in F is theta dot times the direction, which is theta dot F3 and theta dot G3. Okay, now let's write the velocity expansion. We have the velocity of point P in F is equal to the velocity of G in F plus velocity of P in G, and add that to the angular velocity cross the position vector of GP. Okay, and we said earlier that we're defining the point G as fixed to the G frame. And it so happens that we'll align the G point to the pivot point of the bar. Okay, now let's solve each term. The velocity of G in F, okay, is defined as the time derivative of the position vector Fg. Okay. And what is F? And we'll define F as any fixed point in the F frame. So the simplest way to do that is here. That's our F. Okay. Now we have a simpler expression for the position vector RFG as in HT in the F2 direction. Okay, notice that this is the vector RFG. Now we have the velocity of the point G in F as in HT F2 And since these two are the same, okay, now all we have to do is to take the derivative of the scalar term here. H dot t in the F2 direction. Okay, so this is the first term. And the second term, we have here this velocity of point P in the G frame. Okay, now let's go back. And we have the point P as on the bar. And the G frame is defined as fixed to the bar. So the G1 direction will always be aligned with point P. And what we mean by this is the velocity of point P in G is equal to the derivative of the position vector GP. And what is GP? It's k times the direction. So it's the length of the bar times the direction. Okay, and we have k dot G1. Although we can assume the bar does not change its length. So now we have k dot equal to 0. Now the third term, which is the angular velocity of G across the position vector of GP. And as we have shown before, the angular velocity is theta dot G3 or theta dot F3. Okay. And we will choose theta dot G3 because we have the position vector is expressed in the G frame as well. Now what we get is theta k G2. Now all we have to do now is to add the three terms, and we'll have the velocity of P in F as in H dot F2 plus theta dot k G2 hat. Now let's go ahead and find the acceleration of point P in F. And let's use the equation that we have before. Okay, let's work out this term by term. So this is 1, 2, 3, 4, and 5. So the first term is the acceleration of the point G in F, and we already have the velocity of the point G in F as in that, which we have a velocity as h dot F2. And now we can replace the derivative with a V G in F, which gives us H double dot F2. the acceleration point P in G, as we have shown earlier, if we assume that the bar does not change its length, assuming K is a constant, we have arrived at a zero velocity for the point P in the G frame. So here we will just say the acceleration of point P in G is 0. Okay, now the third term. We know the angular acceleration is the derivative of the angular velocity. And we have the angular velocity as in theta dot g3 or theta dot f3 from earlier. The angular acceleration is merely the derivative of the angular acceleration. Okay. And we will use, which is theta dot f3. And since they are in the same direction, we can say theta dot g3. And the position vector, so we have a cross product. And again, from the velocity, we know the position vector, right? And as defined, the G frame is equal to kg1. So now we have theta dot g3 cross kg1, which gives us theta dot k g2. Right. Now the fourth term. We know the angular velocity of G in F, and we also know the velocity of point P in G. Now what we can do is 2 omega gf cross the velocity of P in G is equal to 2 times theta dot g3 cross. And from earlier, we have the velocity of point P in G as in 0. Okay, essentially what we're saying that the Coriolis effect is 0. And the last term, omega gf cross omega gf RGP, which is the centripetal acceleration, is equal to theta dot g3 cross theta dot g3 cross kg1, and it's equal to theta dot square k, and we have g3 cross g1 to g2, and we have g3 cross g2 equal to negative g1. So the direction here is g1, negative g1. Now all we have to do is to add all the terms to get the acceleration of point P in F, which is this should be a minus sign.